Well, hey everyone, my name is Marcus, Developer Relations at Edge and Node, and here we have another Graph Builder's Office Hours. We have the guest Data Detective here today, and they're here today to present to you a really interesting way to use substreams to get token data without using an RPC call. So with that, I'm going to hand this over to them, and Data Detective, take it away.
Hi. Hey guys, we're Data Detective. We're the hackathon team for Denver 2024. And our project involved a substreams powered subgraph that was able to get token data without using any RPC calls. So let's show what that's all about.
All right. So yeah, Data Detective, we're a data indexer and we don't use RPC calls. So we don't use RPC calls because we simulate an EVM instance in our substreams. So just a little background on substreams. They solve the problem of sometimes syncing large subgraphs can take up to months, and they're also not composable. But with substreams, syncing's a lot faster. Substreams are modular as well, so you can swap in and out different components and you can add on to people's and vice versa. So they take in a block, and then there's a map module which kind of acts like a filter. So you just filter through the data, and then you can store and aggregate data that you filtered as you move forward. However, one problem with substreams is that certain things will still require RPC calls, which is a little slow. So there's performance bottlenecks with the speed, especially if you have a lot of RPC calls, that's going to slow things down a lot. And also sometimes RPC calls don't always work. So those two make scalability problems, because if it's slow and the data is not consistent, then that's not really good for scalability. So our solution to fix these problems within substreams is by using EVM core crate, which allows for to simulate the EVM within your substreams. And so this solves the previously mentioned problems. And so now we'll get into the overview, and then I'll hand it over to Ben.
All right. So pretty much how this works is we use deployment bytecode as the contract source code, and use the storage changes from deployment as the contract storage layout. And using this, we can use our EVM core crate and construct a machine instance. And you can pass in encoded function data and dynamically construct function calls and execute function calls locally. So pretty much this is kind of the flow here, is that so we have our map module that takes in the data from the block. From that data, we use that to build contract creation structs, and it'll be a little different depending on if the contract is an ERC20 or ERC721. So we recognize the presence of function signatures in the bytecode to recognize if the contract is ERC20 or ERC721. Then we build a struct accordingly. And then we pass these structs into our process contract functions. We have one for ERC20, one for ERC721. And that essentially is going to call this function here, the execute on function, which that actually has the machine instance in it. And then that will return. So pretty much that's when the machine instance gets built with the storage changes and the deployment bytecode, and then the execution gets run, the value gets returned, and then the process contract where it's used to build the protobuf, and that gets returned, and then back to the map module where then it outputs downstream. So how we build our EVM instance, for this, I can go to some code snippets here. Essentially what we're doing is we're taking the code changes from the contract deployment, and then we're taking the storage changes from the deployment.
Hey guys, I don't want to interrupt, but if you could make the code a little larger so we could see it on our screens, that would be very helpful. Thanks.
Okay, yeah, sure thing.
It's a Control Plus.
Yeah, okay.
Command Shift Plus. Oh, you got it. There you go.
Well, yeah, I got it, guys.
Keep on going a little bit more, please. A little more.
And probably close this out as well.
Yeah.
How's that looking, guys? Yeah.
All right, that's
cool.
Good.
Awesome. Thank you.
All right. Cool. So yeah, essentially our machine instance is built with our contract creation struct. Yeah, it's built with the code, which is the deployment bytecode we get from the code changes that is from the contract deployment, and then we use the storage changes to simulate the storage layout. So this is essentially how we do that. So the first thing we do is we go over the calls and we filter them, and we get only the successful calls. And from these, we use these calls, and we use the from call method and construct our contract creation structs from the calls, and that'll look a little different depending on if it's ERC20 or ERC721. And I will go to ERC20 first since it's a little simpler, more straightforward. So our ERC20 creation struct has the address, which is VECU8, code VECU8, and the storage changes, which are a hash map of H256 to VECU8. And the reason it needs to be a hash map is because we are using it to simulate the storage layout in the contract. So when we get the storage key from the EVM instance, it's going to be an H256. So we need to use that storage key to look up the value that it would be looking up. So essentially, what we do in from call is we identify if the contract is an ERC20, and then we create the struct, and then that gets passed into process ERC20 contract, and in here, this is where we're going to build our protobuf. So right here is our protobuf we instantiate. And right now we're gonna be getting the name, symbol, total supply, and decimals filled out right here. And right now we're just gonna set them to empty strings. So right here, we call the execute on function, and we're passing in the address and the bytecode, the storage changes, and we pass in the encoded function data also. So we do that for name, symbol, decimals, and total supply. So then the execute on function will run the EVM instance, and then the return value is used to populate those fields in the protobuf. So here is how the machine execute on, which is where the machine instance is built. So it starts off just mapping the valid jump destinations. And then here is where the machine instance is instantiated. So we build it using our bytecode here. We have our deployment bytecode, the data, which is the encoded function data. And then we set our stack and memory limit to 1024. And then here is where the execution happens, that in a loop, we essentially step the machine forward one opcode at a time. And it essentially executes the function, and it goes one opcode at a time. And depending on what happens there, we do different things. So OK is going to be the opcode execute successfully, and everything went normal. There's no extra steps needed. It just moves on to the next one. And then here is error, and the error block could be for either exit reason, where it exits for some reason, or a trap case. So right now we have exit reason, which could be, it stopped, it returned, or suicided. So if it's returned, then we return the value returned by the machine instance in this block here. And then we have the exit reasons, and here we have trap. And trap is where we're kind of using our storage changes. Trap means the opcode requires additional input or processing. So, for example, here there is call value, where we just push the H56 initialized to 0 to the stack, and that's just to satisfy just the EVM requirements for call value. We don't actually need any value. Right here is SHA-3. When we encounter SHA-3, we need to, we pop the first two things off the stack, which is the data offset and the data length. And we essentially, then we get from memory, we get, using the data offset and length, we get the storage location from memory, and then we hash that using the SHA-3, and then we push that back to the stack. So essentially what we're doing is when we encounter an opcode that requires additional processing, we just have to do what that opcode does ourselves. So for SHA-3, it pops the top two things off the stack, which is the data offset and memory, and then it looks that up in memory and to get the storage key, and then it hashes that and pushes it back to the stack. So that's what we did here. And for S-load, this is how we're actually getting our token data. is when we encounter an S-load. What an S-load does usually is, well, before an S-load happens, a push happens. And when a push happens, the storage key is pushed onto the stack. So what an S-load does is it pops the top value from the stack, which is going to be the storage key, and then it looks up where that storage key is and gets the value at that storage key, and then it pushes it onto the stack. So that's what we're doing here, is we pop the key from the stack, and that's going to be an H256. And because our EVM instance is not aware of the contract storage layout, that's where our storage changes come in. So when we have the storage key, we look it up here in our hash map, and that's when we get the corresponding value from our storage changes, and then we push that onto the stack as the S-load operation would normally, and then it continues until it's returned. So that is essentially how the EVM execution happens. And then for ERC21, it's very similar but a little more complex. For ERC21, we were to handle some edge cases where tokens were being deployed with the proxy contracts. In the from call, we implemented some logic to recognize proxy contracts, and then we'll just build the struct a little bit differently, where for the instance of a proxy, the code is coming from the implementation and the storage changes are coming from the proxy contract. So in here, as you can see, before we build our struct, we have to pass in for the ERC20 creation, it's a little different. I mean, ERC 721 is a little different than ERC20, is we have to pass in all of the calls. And we do that because we need to analyze the call tree in order to recognize proxy contracts. So what we do is we essentially, same as before, is we'll recognize if it's an ERC 721 contract by the presence of function signatures here. We have the function signature for save transfer from. Name, symbol, token URI, we have the signatures for all those, and we check in the deployment bytecode for the presence of those to identify it. And then if it's an ERC 721, then we, depending on, then we analyze the parent call type here. And we check if it's a delegate call or not delegate call, or if there's no parent call type. So if it's normal and there's no delegate call on the parent call type, then we just build the struct normally with the code from the implementation and the code and storage changes normally from the contract. If it's a delegate call, then we will build the struct with the storage changes from the parent call, which would be the proxy contract. And then for none, we do the same as if it's just a normal call type for the parent call. So that's just a little different about how the ERC 721 works. And also, what's a little different about the ERC 721 is that this is something a new feature we just implemented. We actually just got it working last night. We didn't have this in the hackathon project, but we were able to also get, for ERC 721, we were getting name and symbol, but now we are also getting the token URI link for every individual token ID. So to do that, we have to do things a little differently. So right here, we have our protobuf. Except this is a little differently. It's got more stuff in it. In this, we need the code and the storage changes to be actually in the protobuf for the deployment, because we actually need to store those for later, because we need to run the EVM instance again when we encounter transfers to get the token URI. But for the name and symbol, we get that here. So it essentially works the same, where we just run execute on for name and symbol. And then, execute on will work exactly the same, where we encounter the S load here and pop the storage key from the stack and look it up in our storage changes, and then push it back onto the stack and let it return. So, doing that, we can get our name and symbol. And that's how our name and symbol gets populated in this protobuf here. And then we also have the code and storage changes, and that gets used later. And so this, at the end, this gets returned once we have our token data. From our process contracts, we have our deployment that gets returned, and then we also get our transfers. In the same map module, we have our transfers for ERC20s and ERC 721s. We get all of the transfers, and then that gets outputted from this model in our master protobuf, which has all of the contract deployments for ERC20 and ERC 721, and all of the transfers. So we have a store module here that store ERC 721 contract data, and that just stores the ERC 721 contracts. We're going to have to figure something out about the store limit, but this is just something brand new we just implemented. So it stores the ERC 721 deployment, and then in the map module here, where we have map ERC 721 transfers tokens, this is where we use the EVM instance again to populate the protobuf with token URI. So in this map module, we're building our protobufs for the ERC 721 transfers and the individual ERC 721 tokens. So right now, for the purpose of the demo of the subgraph, since we weren't getting, for this particular one, to get that, once we get the token URI implemented, we didn't have it, that subgraph is now hooked up to the front end. We have another subgraph deployed that's everything except the token URI that's hooked up to the front end. But the token URI one, we just have a subgraph running just for demonstration. And so for this one, I only got ones that were guaranteed to have token URI in them, because we didn't sync from we didn't go back very far in the block range, so we just wanted to have a good amount of examples, just because I deployed the subgraph last night. So yeah, on this map module, we're building our protobufs for the transfers and the NFTs. So in here, this is where we populate it with the token URI. So we get from the store our contract, and we have our get token URI function, which is where the EVM instance is used again. And we pass in our contract from the store and the token ID. So that is this function here, which is similar to the other one for the process ERC 721 contract, but things had to be a little different for this. So this one takes in the contract from the store and the token ID. So it kind of works the same, where except this one, instead of calling execute on, we just build the EVM instance right in this function. So we map the valid jump destination, same as before. And we got our contract storage here, where we build a hash map, because for this, we're getting the storage changes directly as they were from the block. So we got to build the hash map in here. Then we have our code. And we have our token ID. We convert that to a big int. And for our encoded function data, it's just a little different this time, because we need to pass in an argument. The token ID needs to be passed in each time. So other than that, we build our machine instance as normal, and the same thing happens, where it'll go step by step, and depending on how the opcode executes, it'll either be normal or it'll exit. So, or trap. So we wait for the S load, which is same as before. We pop the storage key from the stack, which in this case for token URI, that's usually what a lot of times what they do for a lot of cases is they load the base URI from storage, and that's where you're going to encounter the sload operation. So when the base URI is loaded from storage, works the same, is we pop it from the stack, and we look up the storage key. We pop the storage key from the stack, and then we would look up in our storage changes here and get the base URI. And we have the base URI, we push that to the stack, and then that allows it to execute normally, and then it takes the base URI and concatenates the token ID. In a lot of cases, that's how it works. Sometimes there's other things that are done dynamically to it for the token URI, but then it gets returned. So yeah, we have it returned here. Oh no, we have our return value here. And then and that is what populates the token URI field in the protobuf here. And just for example, we have the subgraph here with a query. And as you see, to zoom in a bit so you guys can see. But as you see right here, we have the token URI for all the unique token IDs. And we can just take this link right here.
Thank you.
Put it in the browser. And here we have our token metadata all right here for every individual NFT in this collection. And yeah, this happened. This mint right here for this particular one had like the very first mint that happened, it was like 300 at once, and we were able to get the token URI for every single one of those without making a single RPC call. Yeah, for all of those at once. So if you wanted to use RPC calls to get token URI in this way, you would have to do it for every individual token ID. Unless you just got the base URI and concatenated the token ID, but that's not going to get every case then, because there's a lot of cases that are not like that. So sometimes if you do it that way, then you're going to have false data sometimes. So yeah, that's pretty much it from my end. Should I give it to JJ?
Yeah. Yeah, so JJ is going to show off the front end and also some of the subgraphs.
Yeah, JJ is going to demo the front end and show to show some of the data we've been getting. So
yeah, exactly. Now Ben showed you how we're getting all this cool data. We can take a look at some. So you guys can see my screen, right? Okay. Can you see my screen? Sorry.
Yeah, we can see it.
Okay, awesome.
Good.
All right. So this is a pretty front end that HN made for us. And we're just calling, I believe we're calling this subgraph right now. So we have our tokens, our ERC20s. We're getting our IDs, our addresses, name, symbol, full slide, decimal, volume, count. This is a bit of an older version where we didn't handle all the edge cases, so we might not have some data here, or potentially these don't have total supplier decimals, but we're still working on handling certain edge cases. We just filter by a couple different things. This is filtering by like transaction count per month, year, and per week, per day. We can see like the oldest deployments where we're missing a lot of data. We're actually filtering out others where we don't have the name here, because some of these are from before the ERC20 standard was fully adopted, I guess you could say. We have the same with ERC 721. So some of the earlier blocks we're missing data, and those are some edge cases that we can't really handle or aren't necessarily worth handling. And then we have the newest deployments as well. And this is not totally synced, so you might like recognize some of these tokens if you've been around for a while, but these are the newest deployments at the current syncing of the subgraph, which is only 32%. But yeah, we have the same data for NFTs here, and we can sort it all. Check out our newest deployments, our oldest deployments. You can also search by a token if you want to look up a specific token. And it'll just return the same data for you. Yeah, and I'll touch on some of these subgraphs now. So as you can see here, we are only at 32% synced on this particular one, and we have 120 million entities. So this is kind of what we were doing in our hackathon project. We probably bit off a little more than we could chew, where we are mapping over every single ERC20 and ERC721 transfer on Ethereum from Genesis. So that's quite a bit of data. We're spitting everything out. So this one's been syncing for a little bit, but it's just getting the contract deployments is really the cool piece. So, for example, this one's just deployments. So it's just getting the token data. So we have this is before we had the token URI for everything. But here we're getting the NFT deployments where we have our name, our symbol, block number. We have some other data like timestamp when it was deployed. Sometimes we're getting the base token URI in these. And then the same for ERC20s here, where we're getting all our relevant data. This is ordered by timestamp. So this one's 88% synced from Genesis. And I deployed this yesterday at 4 p.m. Yeah, so it's been 17 hours, 17 and a half hours. So that's pretty fast to sync from Genesis. And if we were making RPC calls for all 740,000 of these, that would slow down significantly. But this is kind of showing that we can think from Genesis, getting every single ERC20 and ERC721 contract deployment in one subgraph in basically under 24 hours. As long as we get there by 4 p.m., we'll see. And here's one that's synced as well. So this one's fully synced. I think this is an even older version where we're missing some data. But I think this one really shows off the speed. Pretty cool. So we still have edge cases we want to handle. And that's kind of, I'll let them go back because I think they have a couple more slides. So that's our data.
All right. So to wrap up, there's just some future implementations of the EVM core and of some of the possibilities with what we have here. So let's go back to the PowerPoint and just like the last slide.
Yeah, so these are just, possible things that we want to do. This is a brand new thing. This this isn't something that's commonly used in substreams development yet. I mean, we were the first people to use it to make a subgraph. Originally, I got the inspiration for this project. But I was talking to some of the Streaming Fast people about one of the projects I was doing because they were helping me out. And I sent them my project where I was trying to get token data without RPC calls, but I was using regex to try to find name and symbol. And, it worked kind of okay, but I was talking to those guys, and then one of the guys at Streaming Fast, Matt, sent me over to this repo he was working on, where said it was kind of an experimental thing, where that's where he was kind of playing around with using this EVM core crate to get the token name and symbol. So I kind of saw that, and that's like I've been wanting to, play around with that for a while. So I was like reading the repo, studying it up, and reading the documentation for EVM core and all that, figuring out how it works. Then the hackathon was the perfect place to that was our chance to put it to the test. But ever since then, I always thought it would be cool to have a library that allows substreams developers to get all of their token data without making RPC calls, but to make it just as easy for developers to use as implementing RPC calls. and just make it super seamless for anyone to get their data in just a much more efficient and fast way. And also, I want to, we want to experiment with using this to get data for other token standards as well. We just went for ERC20 and ERC721. So that was a good amount to tackle for the hackathon project. But we could really do this for every token standard. So, yeah, pretty much that this is a new thing. And it's a new thing, but it's really cool. And I think there's a lot of, there's still a lot of experimentation that needs to be done, and there needs to be edge cases that are handled. But I think this is a super cool idea, and I'm excited about it. And yeah, I just think there's a lot of cool things that could still be done with this, as people just need to experiment with it.
Yeah.
So, yeah, that's just what I have to say.
All right, and that concludes our presentation. We showed you guys how it works from a low level, what our front end looks like, what our subgraphs look like, how many entities we have. And yeah, it's been really fun working on it.
Yeah, really, really impressive work. I remember being at ETH Denver, seeing this project and just trying to wrap my head around what you guys had done in such a short amount of time. Before people start moving on, I just want to start with a simple question of how can people reach out to you guys if they have any questions, and then we can get into some other questions too.
On Telegram, my handle's Achan1000, AYECHAN.
We'll drop them in the chat. Yeah, we'll drop
yeah.
our Telegram and Discord handles in the chat.
Yeah, that would be the best way to do it. Just drop them in the chat.
Yeah.
I'll be sure to put this on the YouTube video description if anyone wants to go ahead and contact this team. So one thing that I was wondering, okay, this build is very different than any other build I've seen anyone do with substreams. This must have taken, number one, deep knowledge of a substream, deep knowledge of a subgraph, and then thinking outside of the box. Can you, any one of you guys, walk me through how did this idea come up? When was the moment that, or at least a day or a week that you said, let's try for this? Was there anything that really comes to mind about the inspiration for this?
Well, all of us in the house, we're doing substreams development. Yeah, we all got involved with that. So all of us were experienced with substreams. And me in particular, before I got into substreams, I was doing the Ethernaut security challenges for smart contract auditing. I wanted to be an auditor. So I was doing that, and I kind of got that's where I learned low-level EVM knowledge. So that's kind of in substreams, I took an interest kind of in that. I wanted to do things and just get stuff directly from the block, really. And yeah, so my second substreams project, I was tracking variables by storage changes. And then I had the other project where I was trying to loop over the storage changes and use regex. And then, yeah, once I saw the EVM execution repo that Streaming Fast had, that's where I kind of knew I wanted to do something with this. But we actually didn't decide to do this until the hackathon, really, because...
Yeah, the hackathon, we were coming up with ideas, and one of the ideas was a data indexer. Since we had experience building substreams, we thought, we could build really cool substreams as a hackathon project. And Ben knew about the EVM core crate. And so that would be a really sick project if we incorporated that into our data indexer. And that's where we got our idea. The hackathon kind of brought it out of us.
Yeah, it was the hackathon. Because this, when I first heard about it, it was something I wanted to do for a long time, but I never really found the time. I was working on other stuff. And then the hackathon came along, and we wanted a project that suited all three of our strengths as a team. And we were all pretty involved, developing in the graph ecosystem and with substreams and all that. So it just makes sense for us as a hackathon project.
That's great. Yeah, to remove RPC calls is something that can help the entire the graph ecosystem. We're just less reliance on centralized infrastructure out there, and being able to go right to the chain. Such a powerful build. So I want to congratulate you guys on this build. This is really, really impressive. And once again, if anyone out there wants to get in contact with Data Detective and what they are building, go ahead and check the link in the description. Also check out their repo. It is right there in the description as well. See what you can do with this project, which blows my mind. That was done in just a few days. And it's really something that I have never seen and heard of before. So if everyone out there is feeling good about, if there's no more questions, I think we're ready to wrap this up. Any final comments from you guys, Data Detective? I'll let you guys have the last. Floor.
I have a question as well. By the way, I'm just gonna.
Hop in. Go for it.
So, Lil Endian, you seem to have a large hatred of RPC calls. I gotta ask the question: have you ever made an RPC call in your entire Substreams career? Has that ever happened? Have you ever done the, function call generation and made an RPC call? I was just wondering.
No, as of now, I have not.
Okay, I would just like it to go on record that you have
not yet.
Never made an RPC call. That is how devoted to efficiency. But that's all. That was my question. Okay, thank you.
That's a fantastic way to end this. Cheers to moving away from RPC calls for the good of decentralized infrastructure. So, all right, everyone. Well, thank you so much for joining us on the Graph Builders Office Hours. If any builders out there have any builds that they would like to share with us here, we would love to see them. So you could reach out to me on Twitter. It's Marcus_Rein, REIN_, and I'm more than happy to have you guys on. Any builders out there want to stay informed in what's going on in the Graph, go ahead and check out the Graph Builders newsletter. I write that every single month, so builders can stay on top of any news and updates specific to building on the Graph. So thank you so much, everyone, for joining us on the Graph Builders Office Hours. Take care.